Hello everyone, my name is Junling He. In this video, I'm going to present the paper Bridging the Gap Between Anchor-Based and Anchor-Free Detection while Adaptive Training Sample Selection. This paper is about the topic Object Detection. So what is object detection? The object detection task can be defined as given an input image, the task is to locate all objects which we are interested and classify each of them into one of the predefined classes. The object detection task is similar to the object localization and image classification. So what's the difference between them? We all know that in the image classification task, we're given an image of an object. Our job is to classify this image into the right class. For example, given this car image, the image classification task is to classify this image as a car image. In contrast, the object localization task requires not only classify it as a car image, but also we need to localize this car in the image using a bounding box. Different from those two just mentioned tasks, the object detection task often involves localizing multiple objects of different classes using bounding boxes and classify each of them into the right class. For example, if we do the object detection on this image, then we want not only to detect and classify each car, but also the pedestrians, traffic lights, etc. Notice that image classification and object localization involves only one single object, while the object detection typically involves multiple objects. Popular modern object detection methods can be roughly divided into two categories, anchor-based and anchor-free. The authors of the paper compared those two kinds of methods carefully, and they suggest that the essential difference between those two kinds of methods is how to define the positive and the negative training samples. So here is how they develop this statement. In order to compare two different kinds of methods, from each kind they choose a representative method. One is the RetinaNet, which represents the anchor-based method, and the other one is FCOS, which represents the anchor-free method. They observe that these two methods both take advantage of the feature pyramids in order to do the training. So what are the feature pyramids? Recall that in an image classification task, given an input image, a convolutional neural network will learn the features of objects layer by layer, from low-level features to high-level features gradually. Different layers will learn different level of features. The shallow layer will learn low-level features, and the deeper layer will learn high-level features. At the same time, as the layer goes deeper and deeper, the width and height of the layers goes shorter and shorter. As a result, those learned feature layers form a pyramid shape. Therefore, people call those layers feature pyramids. In order to learn features better, both methods don't use those downsampled feature pyramids directly. Instead, they do upsampling to form a new set of feature pyramids and combine these two sets of feature pyramids to get the final feature pyramids which are actually being used in the training. During the training, both RetinaNet and FCOS use neurons in those feature pyramids as their input. The difference is that RetinaNet typically uses a 3x3 sliding window area, which contains 9 neurons to do the classification and bounding box regression, while FCOS only uses a single neuron. Notice that each neuron corresponds to a certain area in the input image. For example, this single neuron, this red one, might correspond to this red area in the input image, while this 3x3 area might correspond to this green area in the input image. Therefore, we can conclude that although RetinaNet and FCOS use different number of neurons as their input, the RetinaNet takes 9 neurons while the FCOS only take 1 neuron. In essential, they do the same thing. They all use patches of the input image to do the training. In fact, their structures are very similar. They all take an image patch as one training sample and pass this image patch through the ConvNet to get the feature pyramids. And then they both use two separate subnets to do the final prediction. One subnet is for the classification, while the other one is for the bounding box regression. The authors of the paper observed that several techniques used in FCOS are actually general techniques which can also be applied to RetinaNet and vice versa. Therefore, in order to compare those two methods fairly and be able to find their essential difference, the authors applied those general techniques on both methods and removed inconsistency between them. For example, for RetinaNet, they choose to only tilt one anchor box per location. As a result, this A here, which represents the number of anchors per location, actually becomes 1, and this A becomes 1 as well. As you can tell from the picture, now their structures in the blue square are almost the same. The only remaining difference now is the different training image patches. Then they did experiments using the modified version of those two methods and compared the results. And they find that there is still a large performance gap between those two methods. In fact, those two methods use different strategies to define positive and negative training samples. RetinaNet used IOU, while FCOS used the spatial and scale constraints. As a result, RetinaNet and the FCOS will choose different training samples in the training. The authors find that if these two methods use the same training sample choosing strategy, that large performance gap disappears. Therefore, the authors conclude that the essential difference between those two methods are the training samples. This picture shows their experimental results. After they identify the essential difference is how to define positive and negative training samples, they propose a new strategy of defining positive and negative training samples. They call their algorithm ATSS, Adaptive Training Sample Selection. Similar to the anchor-based method, ATSS used the notion of anchor box and the IOU strategy to define positive and negative training samples. The main difference is that the anchor-based method set the IOU threshold manually, while the ATSS let the model to decide the IOU threshold by itself. For example, in an anchor-based method, the IOU threshold is usually set to 0.5, which means any anchor box with an IOU value higher than 0.5 would be considered as a positive training sample. In contrast, the IOU threshold is not a hyperparameter in ATSS. In fact, it's a value which is calculated, and each ground truth bounding box in ATSS would have its own IOU threshold value. So here's how it works. For each ground truth bounding box, the ATSS algorithm will first find the k nearest anchor boxes on each feature layer. The k here is a hyperparameter and the distance is measured using the L2 distance between the center of an anchor box and the center of the ground truth bounding box. So let's say there are in total n layers being considered, and for each layer we find k candidate anchor boxes. So for each ground truth bounding box, in total there will be n times k candidate anchor boxes. Then we calculate the mean and standard deviation of IOU value between its candidate boxes and itself. Finally, we sum the mean and standard deviation to get the calculated IOU threshold for a ground truth bounding box. So this is how ATSS learned the IOU threshold by itself. Using the learned IOU threshold, the ATSS can define which are positive samples and which are negative samples. In the paper, the authors also considered one more constraint in defining the positive samples. If an anchor box's center is outside the ground truth bounding box, then it's a negative sample, regardless of its IOU value with the ground truth bounding box. In the paper, the authors also explored the necessity of tilting multiple anchor boxes per location, and their conclusion is quite surprised. They claim that under the traditional IOU-based sample selection strategy, tilting multiple anchor boxes per location is effective. However, this is not the case in ATSS. They said that under the ATSS strategy, tilting more than one anchor box per location is probably useless. They draw their conclusion from their experimental results. So here is their experimental results table. The third and the sixth row represents the result of tilting multiple anchor boxes and the result of tilting one single anchor box respectively. As you can see in the picture, their performance is very close. So in terms of the effectiveness of their proposed method, the authors claim that the ATSS does improve the detection results substantially. They applied the ATSS strategy on both RetinaNet and FCOS, and they showed that by using ATSS, both RetinaNet and FCOS get improved performance. In conclusion, in the paper, the authors first point out that the essential difference between anchor-based and anchor-free method is how to define positive and negative training samples. Then they proposed a novel training samples choosing strategy called ATSS, based on the statistical property of anchor boxes. Also, they showed that when using ATSS, tilting only one anchor box per location is probably good enough. Finally, they also showed that ATSS does improve the detection performance through their experimental results. So that's it. That's my presentation today. Thank you for watching this video. Thank you for your time.